Okay, welcome back everyone to another video, and today we are talking about RAMP. This is the third in a series on RAMP, that is Rapid Assistance in Modelling the Pandemic. And today it's just a couple of points about stuff that has been raised in the previous videos. We're going to just explain them a little bit in a little bit more detail. And the first is to look at the approach or the approaches that RAMP are using. And I want to talk about an analytical approach versus an agent-based approach. And the goal, or one of the goals, is to look at the probability of catching this virus. So we're talking about an analytical approach to finding a probability and an agent-based approach to finding a probability. So I've got my die here, a die, and an analytical approach to uncovering the probability of, say, getting a 5 would involve counting the number of faces on the die, assuming that the die is even, so each face comes up with uniform probability, counting the number of times 5 appears, and then figuring out that the probability of getting a 5 is 1 divided by 6. There's one 5, there's 6 faces, so the chance of getting a 5 is 1 over 6. And that's an analytical or a mathematical, that's what most people would think of when they hear a mathematical analysis. That's the analytical approach. The agent-based approach is essentially to take the die and to blooming well roll it a bunch of times. So if we roll this die 600 times, say, and we observe the 5 coming up 99 times, we could work out from that the probability of the 5 is around about roughly 99 divided by 600, which is roughly 1/6. And that's the agent-based approach, and that is an observed probability. So we've got an analytical approach to finding the probability and an observed approach to finding the probability, because we observe the number of rolls. And that's essentially the difference between a mathematical analysis of the pandemic and an agent-based analysis of the pandemic. It's a bit artificial to separate them because agent-based modelling is a branch of mathematics. But let's leave that to the side. That's the difference, and why are RAMP mostly using agent-based approaches is because agent-based approaches can deal more easily with stuff that mathematical analyses cannot. So mathematical analyses, it's harder to add in detail essentially. So in the last video we talked about the detail in shopping, in supermarkets. So some of the detail we wanted to add in was speeding up. People walk at different rates, and maybe they go faster at the start, they speed up at the start and slow down at the end of their shop. And a mathematical analysis finds that difficult to be incorporated, but actually an agent-based model finds it super easy to incorporate that sort of thing. Now, the other thing that we should note is that an analytical approach very often comes with a bunch of other assumptions, such as large N. So if you've ever read a mathematical analysis, very often it'll say, assume a large N. In other words, in terms of RAMP, assume a large number of people. Now, why does it do that? Well, because the mathematical analysis will break down very often when the numbers are low. So if you do a mathematical analysis of a pandemic, you could end up, when there's only a small number of people, with half a person being infected, or an eighth of a person being infected, or even worse, -1 people being infected. And that's not a criticism, I'm just stating a fact. That is very often what happens when you're doing mathematical analysis, but that will not happen, will never happen when you use agent modelling, as agent modelling is inherently discrete. When you model something using agents, you have got one agent for every person that you're modeling. So it can't get down to half a person. You can't have half an agent. So the other thing we want to talk about is modeling pairs of people. So we consider two people coming together and the probability that one catches from the other, rather than considering 5 people or 10 people. So even if there is a group of 10 people, we still consider the relationship between the infected person and each of the other 9 if there is one infected people. And that is because we are assuming linear transmission. So I want to talk about linear versus nonlinear, because you've all heard about flatten the curve, and you see the curve going up and then it flattens off and then goes down. And you think maybe that's nonlinear, so there's nonlinear transmission within the community. And that's not actually what nonlinear means in terms of analyses. I mean, it could mean that, but it doesn't. So let's look at what it does mean and the implications of this. All right. Let's say I have got an infected person who's red, and they meet an uninfected person who's blue. We are trying to figure out the probability that the blue person picks up COVID from the red person. But what if the situation looks like this? It's not terribly evenly spaced, but that doesn't matter. A linear transmission model would consider the relationship between the red and the first blue guy, and then it would consider the relationship between the red and the second blue guy. And the first guy, would have a chance to get COVID, and then the second guy, would have a chance to get COVID, and that would be a linear analysis. And that's the way that RAMP is working, at least any way that I've seen. That's what they've assumed, and that's almost certainly correct. But what would a nonlinear approach be? Well, a nonlinear approach would say that the probability of this first blue guy picking up COVID is different when there is this second blue guy in the vicinity. So the probability changes depending on how many people there are, and the probability might go up and the probability might go down. Now, why would that be? Well, first of all, let's look at why it might go down. If the red guy is talking to 2 blue guys, and the main source of transmission is moisture from the red guy's mouth, the probability of the blue guys getting it might go down because the red guy is spending half his time talking to the first blue guy and half his time talking and facing the second blue guy. So rather than constantly looking one blue guy in the eyes, he is constantly shifting between the two. So the chance that each of them gets COVID goes down because of the presence of the other guy. So that would be nonlinear transmission, and that would be looking at nonlinear transmission, reducing the probability. What about the other way? Why might it go up? Well, it could go up with a virus, not COVID as far as I know, but it could go up with a virus if it was transmitted immediately from person to person. So if the red guy, through chance, infects the first blue guy, and we then have, all of a sudden, 2 red guys might make it more likely that the other blue guy picks it up. And that would be nonlinear transmission where the probability goes up. And RAMP isn't doing either of those because at the minute we assume that it is linear transmission. So that's why we're dealing with pairs and analysing pairs of people at a time, 2 people at a time, rather than groups like this. And there it is. That's some notes about RAMP.